This episode is brought to you by WeatherGuard Lightning Tech. At WeatherGuard, we make wind turbine lightning protection easy. If you're a wind farm operator, stop settling for damaged turbine blades and constant downtime. Get your uptime back with our Strike Tape lightning protection system. Learn more in today's show notes or visit weatherguardwind.com/striketape.
Welcome back. I'm Alan Hall.
I'm Dan Blewett, and this is the Uptime Podcast, where we talk about wind energy, engineering, lightning protection, and ways to keep your wind turbines running. All right, welcome back. This is the Uptime Podcast. On today's episode, we are going to chat in our first segment about news. We're going to talk about Vestas blades that are still having problems. It sounds like at this point, they're going to shut down a bunch of turbines in a large wind farm. And so Iowa is kind of like the hotbed for investigatory analysis here. So we're going to chat about that a little bit. In our engineering segment today, we're going to talk about high humidity and some of the issues that can cause, especially in offshore wind. Lidar, this is a not new technology, obviously, but the application here on measuring wind turbine speed, especially in remote locations, is really interesting. And lastly, we're going to chat a little bit more about fires and some of the reporting it and some of the implications for people's emotions getting in the way and not wanting their reputations perhaps to be damaged by saying, hey, we have had a fire here and, you know, we need to return that data to the rest of the world. So, Alan, let's jump into Iowa and Vestas. So V110 2 megawatt wind turbines seem to be having some problems.
They are, and it's surprising because it seems like it's relatable to that particular turbine or lightning and the lightning protection system. From news reports, local news reports in Iowa, they seem to be focusing on the lightning protection system. In fact, they've shut down about 45 or 46 turbines in which have indications of lightning strikes near them or to them, because they're concerned about the subsequent structural damage, internal damage to these blades, and whether it's causing some other catastrophic effect, because blades breaking off is really catastrophic from the structural standpoint. I don't know. The question really right now is, what is the possible failure mode? Is it really lightning or is it high winds? Because with lightning strike tends to come high winds. Thunderstorms bring high winds, and we can sometimes confuse that we've had a recent lightning strike with also having a recent storm pass through, and we've overloaded the blade structure and then didn't notice the internal damage that was caused the blade. Don't you think that some of this may be just straight high winds at this point, Dan? It just seems like there's just too many of these issues.
Yeah, I'd be really curious to see what happens in the root cause analysis when they come back with, a reason that this is all happening. But yeah, it seems, I don't know, kind of implausible that lightning is destroying so many of these, right? I mean, they've had a couple,
Right.
Now they're just really nervous that there's some underlying defects, so they want to check them all. But
Right.
yeah, there's too many turbines around where if lightning was causing this many to fail, it'd be more of a problem somewhere else. So it seems more just like either a manufacturing defect, which they probably realize that that's a piece of it at this point, or it just doesn't seem like lightning, even though it obviously is an expensive problem to fix, it doesn't seem like lightning's chopping blades in half that often, right? So there's something else
Right.
at play.
Well, I think these blades are too short to have carbon fiber, and carbon fiber is always seen as the weak link because it is conductive enough to carry lightning energy. And if you have a down conductor system, which almost all blades have, that if you have a down conductor system and carbon fiber, that there can be some bad sparking between the two, which can damage the carbon fiber, or you can overheat the carbon fiber and cause later damage to appear just because of the fatigue on the blades. But on these shorter blades, and I know a V110 is not a small blade, but in relatively speaking, it should just be an all fiberglass blade with a copper down conductor in the middle of the blade. And there's really nothing structurally that should happen there unless the copper is exploding. There's only a very limited subset of things that can happen inside that blade that would cause that kind of structural damage, which leads me to believe that it's not necessarily a lightning issue as it is a high wind situation, which will break blades. We know that it'll break blades, and also I kind of wonder if this is everybody's just being super cautious because they know Vestas has been dealing with a lot of lightning repair. They had that $175 million repair bill to fix a number of wind turbine blades. So your first thought goes to it's some sort of lightning issue. Maybe, may not be, but with this wind turbine company in Iowa essentially shutting down 46 wind turbines, and they're going to go inspect all those, which is going to take a while. Maybe they can see internal damage to these blades and try to correlate it to what the real driver is. And I just have a hard time believing it's lightning. It seems like it's more wind speed or a manufacturing defect. I mean, it could be a manufacturing defect.
Yeah.
Absolutely.
Can you speak a little more to the carbon fiber thing? I think that sounds counterintuitive, where you're saying that this is surprising that, because these are fiberglass, they should be more durable than carbon fiber. That seems counterintuitive because obviously everyone knows that carbon fiber is this incredibly strong and yet lightweight material. So can you speak to why if this was made of carbon fiber, you'd be more likely to accept that it was lightning damage?
Well, carbon fiber is lightweight and it is extremely strong, but it is slightly conductive. It's not as conductive as a piece of copper would be, but it is conductive, and we make all kinds of structures out of carbon fiber that handle lightning energy. Aircraft are designed with carbon fiber all the time and handle lightning energy. What the issue is with carbon fiber and the resin systems that they're encapsulated in. So it's not just the carbon fiber, but it's the epoxy system or whatever resin system they're using for the blade. Because carbon fiber can carry some lightning energy, and carbon fiber doesn't really care. I mean, carbon fiber is essentially burnt material, but the resin system doesn't like getting hot. And carbon fiber is kind of resistive. So as you shove lightning energy down carbon fiber, it gets hot, and the resin system gets over temped. It may vaporize the resin system locally because the temperatures get so hot. And once you do that, you degrade the structural integrity of the blade. So having carbon fiber there provides a pathway to degrade the resin system, i.e. the structure of the blade. Fiberglass won't do that. Fiberglass is non-conductive. So either you're going to punch a hole through it from lightning and cause some sort of explosive effect, or nothing's going to happen because it can't conduct the lightning energy. So in a way, fiberglass is a lot more conducive to controlling lightning than the carbon fiber blades are. It's all about the design. The issue in this particular case, where you have what should be a completely fiberglass blade design, when you have blades get severed somewhere down near the root or the hub, those structures down there are massive fiberglass structures. I mean, it makes other things seem tiny. They're just so thick, and there's no way that lightning energy can travel through them unless it punctures through them. And at that point, it's so thick it probably doesn't do that. So to have them break down near that hub base area indicates that there's something else going on, probably not lightning. And I know we have been involved in a couple of other projects where there have been some questions about lightning strikes causing blade tip separations and some other things. And it turned out, just looking at the raw data, when you start looking at all the data, you realize that the wind speeds were really high relative to having a thunderstorm pass through. So lightning didn't correlate to damage. Wind speed started to correlate to damage. And this is the thing that Alex Byrne brought up from DNVGL the other day when we had her on the podcast was we don't have really good measurements for wind speed on the turbines. So if you do have a high-speed wind event, and you say it's localized, or say, especially in Iowa and the Midwest of the United States, where you can have tornadoes or cyclical wind activity that's local, very, very local, there's really no way to detect that. You wouldn't detect it, except that you would have structural damage to your blades. But you wouldn't have any data to go back and look at necessarily. And that's the trouble. And that's what Alex was pointing out, is that a lot of times we assume a certain kind of failure mode, But because of the lack of data, we really are not sure. And one of the key pieces to determining if we have too high wind loads is have something to measure wind speeds.
Yeah, which we'll cover a little bit later too with the Lidar stuff. So that's an interesting development there. But
it is.
Yeah, you're right. I guess the worst scenario is that this comes back inconclusive, where
yes,
it could be any of three possible scenarios or a confluence of factors, and that's probably the worst. I'm sure at this point they'd like to just identify that it was this. Like, so let's just move past it. But
let me be devil's advocate here for you, Dan. There are 46 wind turbines that have either taken a lightning strike or near lightning strike, so they're on your list of watch. You're going to send a crew out or multiple crews out to go look inside each one of those blades to see, or on the outside of the blade and the inside of the blade probably, to go see if there's some sort of structural defect. You're going to do that once, right? So there's 46 blades one time. Say you come back and you say, I don't really see anything. What, is that the last time you look at them? Probably not. You're probably going to be back there every 2 weeks, every month, because local government officials are going to ask you to keep checking those blades to see if it's a fatigue problem, right? So your best case situation is you identify relatively quickly what this issue is. Otherwise, you're going to be inspecting 46 times 3 blades for the foreseeable future, which if you're the poor technician that has to do that, that's not an enviable job. No way.
Yeah. So obviously, this is not a huge sample size. Like Vestas had a V150 blade break off at an Ohio site recently. We talked about that. I feel like in today, this is just like you compare celebrities today to celebrities back in the past. Like, it's not like celebrities were getting in less trouble personally, like getting caught doing weird things in their personal life. There's just Twitter. There's a phone on everyone right now. So you can't do anything as a celebrity and not have someone film you doing it. Right. And today, like, it's not clear how big of a sample size this is because every blade failure is going to get reported on. Like, it's a big deal. It's a cool photo. It's very ooh and ah, right? So
yeah,
I mean, there's been a couple recently, but as we all know, with just like random chance and variance, if you have 10,000 blades and like say 10, 1%, is that 1%? No, it's 0.1% are going to fail, then you could have 10 fail all in a 1 month period and then none for the next 9 years. Or you could have them all evenly spaced out, one per year over 10 years, right? You just don't know. You could just run bad, just like playing poker or anything else. Variables. So it's still a small sample size, and it's hopefully not a big deal. And they're like, yeah, maybe we just had a weird isolated incident where we just had a bad string of, in the news, and a couple broke all at once, but we should be fine. You just won't really know until they finish that root cause analysis.
Yeah, and there's roughly, just to get your head around it, there's about 60,000 wind turbines in the United States, which means 60 times 3 is 180,000 blades. So having a blade or two break is really, really down on the noise in terms of percentage-wise, and it starts to get to that variability. Is it just random breakage? Not that that's good, but is it just random and it just cluster together because we have some high wind speeds in localized areas that are causing this quote-unquote cluster to appear, but it's not real. It's not a structural issue as much as we're not able to really monitor the winds as much as we can. And and then we have this something that seems much more severe than it really is.
All right, so moving on to our engineering segment here. Alan, let's talk about humidity. So this is an interesting article posted on LinkedIn by Michael Holm. He's the chief commercial officer from Coates. They're a company that makes humidifiers. So he's just talking about some of the things his company does and how much of a problem humidity is inside wind turbines, especially out at sea, which this is a really interesting thing to think about, because I think he's absolutely right that condensation, he said they're removing sometimes 7 liters of water per 24-hour period from the air inside of a turbine, which is crazy to think about. That's a lot of some wet air. But when that condenses on all the metallic surfaces within it, that can cause shorts and all sorts of electrical problems, not even including corrosion and all that stuff. So obviously you're an electrical engineer. How big is this problem of humidity, and is it often talked about?
It is in the electrical world because condensation, particularly salty condensation or conductive, which is what it is, conductive condensation is bad for electrical circuitry. And in a lot of instances, if you open up control cabinets, what you'll see, electrical control cabinets, is you'll see plastic covers and protection means to prevent drips from falling in bad spots. So it's one thing if you're having condensation on the tower, inside the tower, and it's running down the sides of the tower. It's another thing if you have condensation in a control cabinet and you have exposed electrical wiring or exposed electrical components where it can affect the performance of the circuitry. That's a big problem. And the condensation, because it's obviously going to depend on what part of the world you're in and what the temperatures are and what the relative humidity is. And as we get to colder climates, especially with salty air, and you're getting these warm day, cool nights kind of things sort of happening, you can get a lot of condensation inside of wind turbines. We see a very similar thing in aircraft, and I know it's hard to think about an aircraft, but aircraft flies at 30, 40,000 feet, gets really cold soaked, and then we're all going to Disney World. We're flying through, Miami, Fort Lauderdale, Orlando areas, and that cold soaked airplanes, all the water starts to condensate inside of it. And if you're in the right part of the airplane, the back part of the airplane, it's like it's raining in there. There's that much condensation pouring down
That's
inside
so weird.
those airplanes. Yeah, it's really serious. And if you look at a lot of if there's electrical power circuitry and things like that in those uncontrolled atmospheric areas, there are covers and protectors to prevent the water to go into bad places and to drain it out. And there's all kinds of floor drains all over aircraft to suck the water up, because there's a lot of condensation, because it's getting cold soaked and it's flying into high humid conditions. So there's just condensation happens. You're going to have that same sort of effect, not as severe on a wind turbine, but the tower wind turbine is made out of metal, so it's thermally conductive, very thermally conductive. So whatever the outside temperature is pretty much what the tower temperature is, and with the right combination, you're going to get condensation, and that's bad. So there's really two ways to combat it. Try to well, in this particular case, what they're doing is they're drying out the air, cleaning the air, trying to desalinate the air and shove clean air in it. Which is probably the best solution. Another solution is just basically put a dehumidifier in there and just try to suck as much water out of the air as you possibly can. But don't you think, and again, I go back to our discussions with DNVGL, and the argument made about all kinds of systems, that as the megawatts increase and the cost of the turbines increase, the relative cost of dehumidifying systems, lightning protection systems, fire suppression systems, all those other things become relatively small, not inconsequential, but smaller, that it's time to put those systems in just to keep the equipment up and running longer. Because I can't imagine.
Perfect analogy. I got renter's insurance on my laptop because I work on my computer for a living. And as you know, recently I got a new MacBook Air, and like 7 days later left a water bottle, the cap a little bit open, and it filled my new laptop with water. So I learned this valuable lesson, that electronics don't love water, because it certainly didn't turn back on after it was filled to the brim with water. And I learned that the risk of paying $40 a year for laptop insurance was very worth it, because now I didn't have to shell out another $1,200 for a laptop. So perfect analogy. It sounds like this was just meant to happen, so we could relate these two stories here on the podcast. But yeah, no, you're right. I mean, if this is I have no idea what these humidifying systems cost, but if you just end up having major circuit issues and major parts breaking because of condensation, all that, then they're certainly going to end up worth it. Yeah,
they're just complicated air conditioners, right? If you chill the air, you're creating condensation on coils, and then you're taking the water and dumping it overboard, and then you put a filter behind it to hopefully suck out some of the dirt and the crud that wants to blow in. So if you're pushing in drier air, you're forcing out the more humid air all the time. It's just like the way a clean room works. You filter the air, you pressurize the room, and all the dirty air on the outside gets pushed away from the room the whole time. It's a similar sort of concept, so it can't be all that expensive to do, because like I said, it's fundamentally an air conditioner. So I think, relatively speaking, it probably makes a lot of sense long term to put in a dehumidifying system in.
Interesting article out there from Coates and Mr. Holm, who works for the Coates company. So moving on, ZX Lidar has been approved for use on Siemens Gamesa turbines. And their website's really interesting. It says the accuracy. So these I'm getting ahead of myself here. The LiDAR can measure wind speed, especially in remote locations, right? And they can apparently get it right within plus or minus 1 meter per second, or 0.1 meters per second, which is very accurate.
Yeah.
And wind direction to plus or minus 0.5 degrees, so half a degree.
Wow.
So Alan, how does this technology work? What are they measuring, and how does this whole thing tie into making wind turbines more efficient?
So it works in a very similar way to weather radar work, or any sort of radar. If you think about the most simple form of radar you watch on television, they're showing the storms coming in. You can see the colors change. What in the weather radar situation, what they're actually doing is they're sending out a pulse of RF energy out to the sky, and some portion of that gets reflected back, and they measure the time delta to travel out and to travel back, and the intensity of that signal on the backside to then determine how intense that storm is and how far away it is. So think of doing the same thing, except with light, lasers. But instead of bouncing the energy off of water particles in a cloud, you're essentially bouncing it off the dirt and the crud that's in the air. So they're measuring their reflection back and the time it takes to go from A to B off of dirt particles in the air to determine how fast and what direction the air is blowing. It's really ingenious technology, because it's not just measuring it in one particular spot. It can measure it in a lot of different locations simultaneously, nearly simultaneously. So it gives you a real good picture of what the wind looks like coming into the turbine. Now, why do we care, right? Why do we even want that data? Well, one, you can verify the efficiency of the turbine. If you know exactly what the wind speed is and its direction, you can tell if you're pointed correctly into the wind, something you need to know. And then you can look at your power curves versus the wind speeds and see, are we actually generating the amount of power that we should be at this particular wind speed? Those are really important things to know if you're looking to maximize the efficiency of your wind turbine. The other thing that it can allow you to do, and it depends on how far the LiDAR can see out in front of the turbine, is if you do have a tornado situation or hurricane, typhoon, any sort of high wind, twisty wind sort of event, you can give the wind turbine a little bit of a heads up on the control system side and say, hey, look, a big wind gust is coming. Let's feather the blades so that we don't take the full blunt of the wind load on the blade structure and maybe do some structural damage, or to dampen the effect onto the load into the tower, and all kinds of things. If you know what's coming, it's like bracing for, like in football, you see a lineman coming at you, you sort of brace up and get ready to take that hit. This is what the wind turbine would do.
Call your wind turbine children and tell them you love them, because they're not. Yeah. This might be it for you. The farm might be gone.
Right. Well, and I think it has always been, I go back to Alex Byrne again, which she was really about, we need to have more data of what's going on each of the wind turbine sites so we can then analyze the data properly. And with LiDAR, you're going to get a lot of data, very accurate data, to determine the efficiency of your wind turbine system, one, but also maybe to prevent some of these structural damage events from happening, which is super important. So again, as the wind turbines get larger and become more expensive to install, it starts to make sense for some of these Delta small systems safety features to be installed to protect your investment. And I think LiDAR is one of them. That's why you see Siemens Gamesa, basically blessing a particular version of a LiDAR system as being good for this wind turbine, and probably because it interfaces with their control systems. I'm guessing that's probably part of the deal, is that they can integrate into the system. Yeah,
and this version is the ZXTM. So, and they said, it has to be agreed on, by the customer, whether they can use both parties need to say, okay, we're fine with verifying the speed with LiDAR instead of the the mast and the anemometer. So
yeah, which is a very clunky system, and that's a 1910-ish 1880 kind of wind vane on top of the barn system of detecting wind direction and wind speeds. it's antiquated because it's not accurate, and it's measuring it after it goes by the blades. So the event has already happened when already to the load. So if you do have some sort of high wind microburst kind of event, it's already too late. By the time you measure it, the wind's already by you. So you can't react to it versus a LiDAR, which you can see out front and then adapt, which is a huge delta in terms of increasing blade longevity and blade safety and efficiency and all kinds of other things. It just makes sense to get to a LiDAR solution.
So our last topic for today, interesting article from windpowermonthly.com, just talking about underreported wind turbine fires. And the headline here is "Fires at Wind Farms Underreported Over Fears of Reputational Damage." So this is something I think we've talked about sort of as a recurring theme that, you know, wind turbine manufacturers are keeping all of their data close to the vest. So you don't really know who's solving what problem how, right? They don't want to,
Right.
And it seems like that's kind of hurting everyone's ability to grow as an industry. Like, hey, we could share a little bit of data or a little bit of our data, then we could solve some of these problems together and move forward. But also, this is just getting into human psychology a little bit, where people don't really want to admit that they're having problems, right? It just goes beyond the data. You know, there's no like data secrecy issue there. They just don't want to admit that, yeah, maybe wind energy is not as safe. I mean, it is very safe, but maybe it's, you know, this is all just data that's saying like that there are issues, which there's issues with everything, right? How many car accidents are there every day? We don't need to, you know, screw up the, you know, fudge the data on car accidents. Like we know that there's a certain amount that happen and hopefully get safer over time, but there are car accidents. There's, you know, plane crashes, and there's issues with wind turbines, including fires. So does this surprise you that maybe there's a little bit of underreporting?
Well, I think there's probably underreporting in terms of if they're claiming with the insurance company. That may be part of it. It's just like in an automobile accident or some sort of home accident. If the damage is low, you're not going to claim it, so nobody really knows the wiser, and you fix it and move on. Maybe not realizing there's more of a larger root problem to what created that fire. And then I think also in the United States in particular, because it's a pretty big country and it's very state and localized, and fire departments tend to be very local also, and not really connected in a sense that they're providing data to the rest of the world. So I can't necessarily go online and look and say, hey, what happened in this small town in West Texas in terms of fires? I don't know if that data is really accessible. And unless a local news station or television station reports it, you may not have any sort of record of a fire occurring if the fire department doesn't sort of broadcast it out. So it's really going to be really hard to tell how many fires there are on wind turbines in the United States, and the same would exist in Canada and other places, that you just don't really have a reporting system for it. I think the key, though, is realizing as an industry, and this is where groups like eSig and some of the other groups that are focused on industry needs and industry data and sharing of information, those are the forums in which I think are important. That even in the automotive world, I think automotive world, they've shared data between the manufacturers about general problems, motorist driving habits, and that sort of thing. That if you can share data amongst one another, you can most likely eliminate some of these problems, or you can identify them ahead of time so you can address them. Because with any fire, you have to have some sort of overheat situation combined with some sort of fuel, combined with oxygen, which you always have oxygen for the most part. So you just need that heat, and you need that fuel, grease, bearing heat, all kinds of other issues can be a problem. And, you know, it's just, again, we get back to, are fire suppression systems needed? Well, it depends on how many fires there are and what the cost of those fires are. And until we get a really good handle on what those fires are, how big they are, how expensive they are, how many they are, it's going to be really hard to justify one way or the other.
All right, well, we're going to wrap up today's episode of Uptime. If you're new to the show, welcome. If you're a regular here, thank you for your continued support. Please subscribe to the show and leave a review on iTunes, Spotify, or wherever you listen to podcasts. Don't forget to check out the WeatherGuard Lightning Tech YouTube channel for video episodes, full interviews, and short clips from each show. For Alan and all of us at WeatherGuard, stay safe and we'll see you next week. Is downtime causing you financial pain and putting a stop to your power production for months on end? It's no secret, lightning strike damage is a major cause of wind turbine downtime. This damage is preventable with our easy-to-install strike tape lightning protection system for wind turbine blades. Our incredible engineering, build quality, materials, and edge sealants withstand up to 5 times more abuse in the toughest weather and lightning conditions. And we've got the research to prove it. If you're tired of constant downtime, we can help. Reach out to us at weatherguardwind.com and schedule a free call. We'll get your uptime back in no time.